Hello class, today we're going to talk about equivalent expressions. So with equivalent expressions we have things called terms, and these terms are part of an algebraic expression that is separated by addition and subtraction. Okay, so then our next thing we want to talk about is our like terms. The like terms are things that are being multiplied by equivalent variables. Sometimes we'll have multiple terms in a problem, and if they're being multiplied by the same variable, we can use them and just put them together. So for an example, we could have 4x plus 3 plus x, and what we can do is we can create an equivalent expression to this by putting like terms together. So we can see that this and this are the same terms, right? They are like terms. So our 4x and our x are all like terms. Because they both are being multiplied by the variable x. So what I'm going to do is I'm going to use my commutative property to switch my 3 and my 4x so that now I have my 4x and my x next to each other. Now the thing about seeing a term, a variable, all on its own, we can think of it as being multiplied by 1, okay, because it's 1 times x is going to give me x. So I can think about that 1 being there, and now what I can do is I think about multiplication being, as we've talked about, repeated addition. So I'm just taking that x and I'm adding it together 4 times to get 4x. Then I have addition of 1 more x. So I can take that and add 1 more x, so that you can see I have 5 x's. So I put those together and I bring down that constant, that the 3 does not get added with the 5 because my order of operations says this multiplication has to happen before I can add 3. But since I don't know what x is, that's as small as I can make this expression. So that is what I would finalize as my equivalent expression. Okay, that would be the simplest form of that expression. So do one more example of that. We could have something like 6n plus 2n minus 3. So now, again, multiplication is just repeated addition. So if I'm doing 6 n's, I would take n plus n plus n plus n plus n plus n. I got 6 n's. I'm adding 2 more n's. So there's 2 more n's. And now what I'm doing is I'm actually adding together 8 different n's. So this 6n plus 2n becomes 8 n's. And then I have minus 3. Notice the 3 cannot be put in here. I cannot do 8 minus 3 and have 5n because 3 is not being multiplied by n. As we said before up here, my order of operations says this multiplication has to happen before I can subtract 3. Without knowing what n is, means I have to leave it how it is, which means this is my answer. That is how we simplify that expression. So as we continue further, we can use other properties that we know. Properties like our distributive property. If we use the distributive property, if we are given an expression that says 4 times b plus 3, what we would do to simplify this is to distribute my 4 through. Okay, so I'm finding another expression that is equal to 4 times b plus 3. So I use the distributive property, so I get 4 times b, I do 4 times 3, and I get 12. So that is my equivalent expression to 4b plus 3. Okay. Another way we could go about looking at this is sometimes we have to factor things, and we have to find what we call the greatest common factor. Okay, and you're going to hear me refer to it as the GCF. Okay, when looking for our GCF, so if we have, maybe we're given an expression, we're told to find another expression that's equivalent to it. So if I'm told I have 27y plus 18n, what I have to do is I want to find my greatest common factor. So my best way of doing this is creating a factor tree. Alright, because this is what I want to do. I want to reverse distributive factor. And so in order to do that, I have to find my greatest common factor. So what I do is I do factor trees. I got 27y. What two things can I multiply to get 27 and y? The first thing I always do, separate out my variable. So 27 and y. Then I think of two things I can multiply to get 27. And the key here is not 1 times 27. That will get us nowhere. There's no point in doing that. If I'm multiplying it by 1, not worth our time. But I do know that 3 times 9 gets me 27. 3 right here, that's as small as it can go. Okay? All I can do is 3 and 1. 3 and 1. There's nothing smaller here, so I leave that alone. That's as far as we can go for our greatest common factor here. As I can continue with the 9. I can separate that into two 3's. Now I'm down to as small as I can go with my factor tree. Okay? So then I look at the other term that I have, 18 and n. Again, I want to separate out my variable from my number, because n times 18 is going to get me 18n. So separate out the n, and then I start to separate my 18. I know I can do 2 times 9 to get 18. 2 is as small as it can go, so I know I'm good with that one. 9 can be separated into 3 and 3. And so now I'm as small as I can go at the bottom of all those factors. I have found their roots. Now what I need to do to find the greatest common factor is find what do they have in common. Do they both have a y? No, there's no y. Does it have a 3? Yes, there's a 3. So that's in common. Move to the next one. Does it have another 3? Yes, it does have another 3. So those are in common. Is there another 3? No, there isn't. So what I can see is I have two 3's in common, which means I take that. So if I've circled two 3's, I can do 3 times 3. So I multiply everything I get. Everything I circle on one side, because it's the same thing that I circled over here, I get 9. 9 is the GCF. Okay, it is the greatest common factor. Which means when I go to undistribute this expression, my 9 gets pulled out, and now I'm multiplying to see what's left. So what's left in my 27y is 3 and y. So I multiply 3 times y, and I have 3y. I add what's left of my 18. And so I've circled both those, so all that's left is 2 and n. Notice I don't include these ones, because they have roots coming off of them. If there are roots coming off the number, we don't include it. And so that's why those get ignored, and we multiply 2 and n. And so now I have 9 times 3y plus 2n. And so that is equivalent to this expression. So that's how I find another equivalent expression to 27y plus 18n. I have to pull out my greatest common factor and then fill in with what's left in the factor tree. So 2n, 2n, 3y, 3y. Alright. If you need any help, please make sure to let me know. Ask me questions on the chat. Send me emails, whatever you gotta do to make sure you get the help you need.